Hello, salams, and good morning. Welcome to Computational Thinking, Tuesday morning edition at IBA City Campus. My name is Jawad Ahmed Fareed, and I will be your host for the next 14 weeks. Why bother with computational thinking? Let's start with a short anecdote about how I got into computer science. When I was a high school student, as an 18-year-old, computer science was not on my list. I didn't want to be a computer scientist, not a profession I thought about or given or allocated any bandwidth to. My preferred choice was to become a fellow society of actuary. And in those days, the only way to become an actuary was to take these exams offered by the Society of Actuaries, or SOA for short. The only way to pass these exams was to go through these thick textbooks on calculus, statistics, inference, computational methods, numerical analysis, linear algebra, differential equations, partial differential equations. As a 18-year-old, it was only natural for me to think and ask if there was a shortcut, if there was a hack that I could use to apply and take these exams and pass them without actually studying the textbooks. Turns out that there was a hack, and that hack was to enroll into a local computer science program that covered the same curriculum. So I didn't put too much thought into it. I saw the hack, I took it, and it was very useful. 35 years later, when I look back, I find it both interesting, amusing, and funny that I missed a very strong connection between actuarial science and computer science. Obviously, there's a science, so actuarial science and actuarial science and computer science. Science is the key common word between them. But the interesting thing that I missed out and that you should possibly look up is that actuary started off as human calculators all the way back in the 16th century. I hope you can see the irony. I was aware of the fact that I was studying to become a human calculator by enrolling in a program dedicated and devoted to building inorganic, inhuman, and artificial computers, otherwise known as calculating machines. I spent about 6 years working in the consulting profession as both a computer scientist and an actuary. And then I figured out that there was a non-technical side that I hadn't covered very well, either as part of my CS education or as part of my actual education. And to do the things that I needed to do, it was important for me to fill in those gaps, and that's how I ended up with an MBA from Columbia. My ultimate specialty or specialization became something known as computational finance, a space, an area that sits at the intersection of both finance, economics, statistics, and computer science, which is the reason why I feel very, very strongly about the field of computational thinking. I think there are algorithms all around us. I think that you're aware, that you know that there are algorithms all around us, but we don't spend enough bandwidth on them. And the reason why I love the subject and the topic of computational thinking is I think it's a great time, it's a great opportunity for us to explore and think more deeply about the process of computation. Now, there are other advanced courses that you're going to cover as part of your CS education. The objective of this course is to get you started thinking about some of these themes. The more time you spend thinking about these themes, these topics, and these questions, the better prepared you would be for the application of these topics, the advanced treatment of these topics when that pops up in your curriculum and your course later down in your degree program. And with that, let's start. What exactly is computational thinking? Computational thinking is just a fancy word for solving problems. It's a tool, a mindset, a framework, a collection of frameworks that we use to solve problems. What does it take to solve problems? To solve problems, I think your starting point, and this is the most important point, is what is it that you're trying to do? What are the goals and objectives of addressing this challenge? And I would simplify this, and this would essentially become what I call the why question. Asking the why question is an important step in problem solving because it allows us to explore other ancillary areas of our problem statement that we may not necessarily be aware of. One of those areas is resources. What are the resources that we can use to solve these problems? A third area are restrictions and limitations. What is it that we can or cannot do? A fourth area is our prior history with the problem in question. Have we done this before? Are we aware of what it takes? What does it look like? What approaches have we tried in the past, and when have we failed with them? What has been the experience of others when they've tried to attempt similar problems? If you put this together, collate this together, this is what it looks like. Solving problems essentially requires us to look at 3-4 areas. One is objective and goal, one is constraints, limitation and restriction, one is resources, one is our history of solving similar problems in the past. Let's take a very simple example. You want to get from DHA, Karachi, to IBA in 30 minutes. This is my problem statement and objective. Is that possible? Now, I need to be a little bit more specific. So DHA is a broad space and IBA is a broad space. I need to specify exactly which part of DHA and which campus of IBA are we talking about. Let's start with a very simple example of coming all the way from the other end of town, which is essentially Imar, right next to Dodariya at the tip of Karachi, to main campus on the other side of town. Can you do this in 30 minutes? So the objective and end goal here is, can you go from Imar in DHA to IBA main campus in KU, in Karachi University in 30 minutes? Is that possible or not? That's the question. Are there any restrictions and limitations? Yes. You must arrive before 8:15 a.m. in the morning, and you must do this Monday to Friday. You're looking at main campus, not city campus, and your departure time cannot be any earlier than 7:30 a.m. because that is when the point your ride, your driver, your car, your commute becomes viable. Do we have a history of solving similar problems? In your case, no. You may have come to the campus to take the test, you may have come to the campus for orientation, but most of those instances and variations were actually not part of your problem set. You came and took the exam, the test, the admission test, the application test at IBA on a weekend, so not relevant. You came for the orientation on days when the campus was closed to other students, so only you were allowed. So you didn't have the full traffic load of students coming in to the campus on those days. This week, your first week coming to IBA is when you actually see everything at work under real life conditions, not simulated conditions, not easy conditions, not conditions that are supposed to sort of make it easier for you to solve the problems, but actual real life conditions. And that is going to change how you pick your path for commuting to IBA. One part of it is going to be your familiarity with the path. One is the approach. One is, what are you solving for? Are you solving for speed, time, mileage, comfort, stress, absence of stress, and your confidence in making sure that you hit your end goal? Remember, what's the end goal? The end goal is this one, 8:15 a.m. estimated time of arrival at IBA's main campus. There's another reason why introduction to computing is very important in the freshman year. There's an enormous amount of work that you have to do in the first year, both in the first term and in the second term, that focuses on exposing you to the concept of programming. And in programming, the common challenge, the most common challenge, the challenge I faced also when I started in CS is, how do I solve this problem? I've given you a statement, you need to figure out how to crack it. Where do I start? What are the attack vectors I can use to figure out the right solution, a solution that works, a solution that sort of gets me past the test cases specified for this specific piece of code? So there are 3 stages in this process, and I've sort of broken them down into what I call level 1, level 2, and level 3. So the level 1 framework are generally very simple, very linear frameworks. For example, the first framework is input, output, and process. If we take the example of our commute from Imar DHA to IBA Karachi, what's the input? Go back to the problem statement. What's the input? The input is from DHA to IBA in 30 minutes. That's the objective and end goal. So you're sure about that. Your ETA, which is your arrival time. Your timeline, which is Monday to Friday. Your destination, which is the main campus. Your constraint and restriction, which is, no earlier than 7:30. What's the output? The output is a proposed path. What's the process? The process is the process that allows you to go from A to B, from point A to point B. So that's one part. A second part in the level 1 framework is identifying smaller subproblems. So when you do start off in the morning, a smaller subproblem is, okay, if I'm starting off from EMAR, what's the fastest way for me to get out of DHA past the school districts? Why is the school district important? Because of school rush hour traffic. So you don't want to get caught in that traffic on the wrong side. You want to bypass and skip that traffic. So where are the schools? What are the school zones? What are their opening and closing times? And are they bang in the middle of my path? And if they are in the middle of my path, how do I avoid the path, right? That's one part. Once you're out of DHA, you hit Shara FSL. Now from Shara FSL to IBA is another set of choices. How do I get from Shara FSL to IBA? I can go through Sindhi Muslim, I can go through Karsaz, I can go through Shahid Millat, I can go through Shabirabad, I can go through Tipu Sultan, I can go through Rashid Manas, I can go through Rashid Manas and Muskan, I can go through Rashid Manas and Nipa, I can do Karsaz and Hassan Square. These are all variations. But what you're doing is you're breaking it down into smaller steps and smaller sequences. And then the last part is what I call a work breakdown structure. Once you figure out what the input-output process is, once you figure out what the smaller subproblems are, what are the things that you have to do for you to solve the problem. In most instances, the sequence essentially becomes, we use this to specify and get a better sense of the problem statement. We use this to break down into smaller problems. And then for each subproblem, we go out and create a work breakdown structure, our task list. Here is what I have to do to solve the smaller problems. In terms of framework and thinking, what you really want to do is you want to keep on running this process, breaking it down into smaller subproblems till you get to a stage where you have an effective work breakdown structure that you can translate into a sequence of actions and steps so that you can go ahead and solve one small subproblem. And once you've solved that one small subproblem, then you can move on to the next one, then the next one, then the next one. When you solve all subproblems, you solve the bigger problem. Once you solve the bigger problem, you have to ask yourself, okay, is this the only problem, or is there a higher level that exists beyond this problem that I need to address? Fair enough? So this is a tactical approach. This tactical approach allows us to execute on the work that we need to do. But then there is a second layer, and while the tactical approach, so I call this my tactical approach. Let me write this down. Tactical. My tactical approach tends to be fairly linear. But then there's a non-linear side to my thinking, and that thinking is what I call a level 2 process. The level 2 process has 5. I only have 4 here, but there's a 5th one that you're going to see when I go through the detailed breakdown of these slides. The 4 elements within that are abstraction, pattern recognition, decomposition, and design. Abstraction is essentially essence. So we will come back to this word a little later. What is the essence of the problem? Pattern recognition is, have we done this before? Are there any lessons that we learned from our prior experience? Is there something that we've done before that can be reused to solve this specific problem? Is there a path that we've tried in the path that has failed, that has not really worked, and so on. Decomposition is essentially this, is work breakdown structure. How do I break this down into smaller subtasks and smaller problems? And then how do I break those subproblems and subtasks into smaller and yet smaller subtasks till I get to a point where I have what I call an atomic transaction. A transaction, a sequence, a step, an event, an action that I can execute on my own at one small level. The fourth and final piece is design. Design is generally a response to our environment, to deliverables, to a higher level of thinking which focuses on what else is there. When we ask the why question, when we ask the who question, what else is there that we haven't captured in the first 2 processes, but that what else is there which is not stated in the problem statement, but would still be required to solve the problem. What is missing but is assumed to be understood. While level 1 is linear, level 2 in most instances is non-linear, level 3 is a completely different dimension by itself. These are the 3 processes. these are the three stages, these are the three levels and layers of thinking that we'll be focusing on in our course on computational thinking. And we'll be doing that by looking at this 14-week journey essentially as a journey of exploration. So the first week, which is this class, is focused on computational thinking. Week 2, when you come back, we'll focus on visual thinking. Week 3 and 4 are focused on data, Excel, and the concept of business intelligence. Week 5 and 6 is patterns in code and data and efficient problem solving. Week 8 is an intro to game AI, and we'll talk about this a little later when we talk about Scrabble. Week 10 is also game AI. 11 is about the industry, domain, career, skill paths, choices that you have to make, choices that you should be aware of with respect to your interest, with respect to your interests in the field of computer science when it comes to picking a career. And then outside of these themes, week 9 focuses on hardware and architecture. There are a couple of key elements that you should be aware of when you think in terms of computational thinking, deployment of computational thinking. There is some math in week 7 here and here. It's not really math, it's basically math as applies to the field of computer science, and that focuses more not so much on mathematical expression, but how does that math relate to the soul of CS and the intersection of computer science with other fields in the world. And that in essence is the summary of the path, the journey. That in essence is the summary of the path, the journey that we'd like you to explore over the next 14 weeks. Now, beyond the curriculum, there is a bit of extracurricular stuff that you have to do, which is again there to create an environment of exploration on your part. In that list, there are 2 game jams. So there's one game jam with Mindstorm Studios, and this game jam is going to happen on 22nd, 23rd, and 24th. This is a weekend. Please log these dates. This is a mandatory game jam. Every section of IDC will be participating in it. This is a graded exercise. This will become part of your final grade in this specific course. There's a second game jam with Mindstorm Studio, but this is not mandatory. This is by invitation only. Your invitation here would depend on how you fare here. The dates for this are 27th, 28th, and 29th. This is immediately the weekend after we come back from our midterm break. There is also a series of speaker sessions. The first external speaker session is on main campus on 25th August at 5:30 p.m. The location for this has changed. This is now going to be MCS 3 in Amman CED on the ground floor on 25th evening on the main campus. So this is main campus. That covers the review of the curriculum. Let's take a look at the Four Horsemen, the 4 components of the level 2 process that we spoke about earlier. So what is abstraction? Abstraction, decomposition, pattern recognition, and design. Abstraction essentially focuses on the essence. What is different? What is relevant? What is irrelevant? Whatever is irrelevant, take it out. Decomposition is your work breakdown structure, your task list, and your subtasks. Pattern recognition is if you're doing something again and again, is there a repeating sequence that you can identify, and can you generalize that repeating sequence so that you can reuse it again the next time you need to do something similar? Design is essentially how does the recipe change based on what are we solving for? Are we solving for speed? If you remember your IBA to EMAR or EMAR to IBA journey, the selection of your path is a function of what is it that you like doing when you're driving. Do you want to get the best mileage? What does the best mileage mean? In your car, in your automobile, in your bike, in your ride, is the best mileage a function of driving slow or driving without brakes? If you are trying to drive without brakes, then even though you'd get the best possible mileage, it is possible that the path may be a little longer. Path may be a little longer, but you may get better mileage, so your actual cost per mile or cost per kilometer may be lower given the fact that you have better mileage, and your time to arrival may actually be a much closer to your original specified time compared to a path which has a shorter distance but has a lot more traffic. So what are you solving for? Are you solving for mileage? Are you solving for speed? Are you solving for efficiency? Are you solving for stress? Are you solving for time to destination? Are you solving for getting to the destination without losing your mind, given the fact that you've just gotten stuck in traffic for 15 minutes and you're getting stressed about the fact whether you'll make it to your class on time or not? So all of that falls under the design element. Let's take a look at all of these one by one. So the first one is focus. Focus on what is necessary, focus on the right level of detail, focus on understanding that there are different levels that exist that will ultimately allow you to solve this problem, and ignore what is irrelevant at any given level. How does abstraction solve with problem solving? Let me give you a very simple example. Not from the field of computer science, not from the field of programming, not from the field of computational thinking, but I think it still is a very relevant example. Assume you're an author. You write books for a living. Assume you've been writing books for 50 years. Assume you're a very successful author. You're a world-known name. Assume you're Stephen King. As Stephen King, you say, okay, I've written a lot of books and a lot of people ask me about the process of writing, so I'm going to write a book on the process of writing. And you write that book. And the book is a big, big success, huge success. It's possibly the best book that you've ever written in your life. It is about the craft of writing. It's actually called On Writing. Stephen King on Writing. What do you think the essence of that book would be? So say about 300, 350 pages, you want to summarize that book, the essence of that book in a single line. That is the process of abstraction. Does that make sense? Process of abstraction focuses on the essence. What is the essence of solving this problem? What is the essence of solving the problem of learning to write well? The essence of solving the problem of learning to write well enough so that the world would want to buy and read your books, according to Stephen King, is this. In On Writing, Stephen King says that if you don't have time to read, you don't have time or the tools to write. Paraphrasing, not the exact quote, but that's the essence. If you want to learn to write well, start by reading. If you're not willing to read, if you don't want to be a reader, if you don't enjoy being a reader, you are not going to be a world-class writer. Simple as that. That's all there is to it. That's the essence of the book On Writing by Stephen King, essentially on the craft and art of writing, and the essence of his 50 plus year long career of being a successful world-class author. What is the essence of that career? The essence of that career is the book. And what is the essence of this book? The essence of this book is, if you want to be a writer, read. If you can't read, don't want to read, are not happy with reading, don't like reading, you can forget about writing. So abstraction. What is abstraction? Focus. Focus on the relevant. What is relevant? If you want to write, read. Let's move on to number 2, decomposition. Decomposition. Our example, EMR to IBA. So in our journey from EMR to IBA, we have to make a list of things we have to do to get from EMR to IBA, right? But can we extend this? Essentially, we're saying it's a task list. It's a recipe. Let's see if we can put this recipe to work. A task list, a recipe. Let's see if we can find an illustration of a recipe. So a haiku. A haiku is a Japanese art form, a form of expression, a poem that essentially refers to a moment in time. And it has a very simplistic structure that sounds and looks very simple, but leads to some really interesting results. So as an example, we're just going to do a simple check, and that check is going to be, you're going to write a haiku, test the haiku, and then you're going to publish the haiku. But you're going to do this in your working break. So the break that you have for 15 minutes between the class, you will use that to think about the haiku. When you come back, you will share the haiku that you've written in the class. If you extend the example to haiku to the scores, when you put together the scores, how many of you, if you extend the example of haiku to creating the scores, how would you teach a course on computational thinking? What would be the essence of your theme? What would be the task list? What would you focus on? And I think at a high level, if you remember the orientation on ITC that we gave on day 2 of your orientation at the School of Math and Computer Science, this is what we spoke about. The course is about thinking. Thinking is a function of the path you walk. So it's also about putting you, getting you, convincing you to explore alternate paths. Paths are important because the experience that you see on those paths, the experiences that you go through on those paths transform your thinking. How do they transform your thinking? They transform your thinking by making it possible to see stuff. Why is that important? It's important because you can only count stuff that you can see. But that requires you to learn to see things that you were not able to see before that. Why is counting important? Counting is important because in the field of computer science, in computational thinking, we're very interested, we're very keen on stuff that breaks our code. Code generally breaks at boundary conditions. If you've not learned to think, if you've not learned to see or spend time thinking about boundary conditions, your code will break. So that's one part. This is one part of the design of the course. If I'm teaching a course on computational thinking, I want you to think by exploring paths that you've not explored before, go through transformative experiences that show you how to see, to think about things that you normally not think about before in your life, especially with a focus on what we call boundary conditions. And then side by side with this, there are 3 other areas that are really important. One is I want you to think about what do your users of the software, of the code that you will write want, which then brings you into design. Design is important. Why? Because design allows you to have the empathy to explore this question, this conversation around the topic of want. And then all of this boils down to bringing together these themes in an intelligent fashion. But you can't do that unless and until you can answer a core question on what really is intelligence. How do we define it and how do we work with it? What is this? This is a breakdown of the course. What we've just done is, if I want to teach a course on computational thinking, I want to identify key themes, key elements that I want to cover in the course. And by breaking this down into this framework, 1, 2, 3, 4, 5, 6, 7, 8, I've identified 8 themes that I want to emphasize in the next 14 weeks. Back to your haiku. A 15-minute break that we have between the 2 sections of this class, use that break to think about how you're going to write the haiku. Now, to write the haiku, once you've written the haiku, you have to validate it on writeahaiku.com. Why write a haiku? Because there's joy to be found in being concise, poetic, and to the point in less than 3 lines and 17 syllables. Is there a recipe? Of course there is. Here's the recipe. The rules are very simple. 3 lines. 5 syllables in the first and third line, 7 syllables in the second line. The lines don't rhyme. Remember this. It includes a cutting word and includes a reference to a point or a season. Do we have examples? So here are 2. The first one, hospital nights, whispered goodbyes, wailing monitors, silent steps of grief. What do you think this refers to? Hospital nights, whispered goodbyes, wailing monitors, silent steps of grief. What does this refer to? A haiku refers to a moment of time. What is this moment of time? Can you guess? That's one. And there's the second one. The second one is, but for love, sleep feels like a warm blanket from the land of death and dying. So if the first one was about death, what do you think the second one's about? I'll let you guess what the second one's about. So, very serious season, moment in time, grief, death, and sickness, both of them, this one as well as this one, is essentially inspired by stays in hospitals, one as an observer, one as a patient. But there are other haikus. So that's two. So this is example number one. Hospital nights, whispered goodbyes, wailing monitors, silent steps of grief. This is example number two, which is but for love, sleep feels like a warm blanket from the land of death and dying. That's two. Here's the third one. I'm so tired. Where did all my money go? My back is hurting. I didn't write this. So the first two I wrote, this one I haven't written. What do you think this refers to? I'll let you guess. So you can figure out what this refers to. When we meet in the class, you can always ask me and I'd be happy to answer the question. What does this refer? It may mean different things to different people depending on their mindset and their time of life and that specific time of the month, right? For me, I'm so tired, where did all my money go? My back is hurting. Represents the end of the month when we're waiting for payroll to get processed. I'm so tired. I work so hard. I'm so tired. Where did all my money go? My back is hurting. All right. So that's three instances, three variations. This is variation number 3. I am so tired. Where did all my money go? My back is hurting. Didn't write this. Stole it from Twitter. I think I have a Twitter friend that I've never met in my life, but I follow her and she shares really interesting stuff on a regular basis, which reminds me, if you're not on Twitter, you should be on Twitter despite everything you read about Twitter, and also known as X. Number 3, pattern recognition. Identify elements for reuse for problem solving. Remember the DHA IBA example? Your experience is going to depend on what time you travel from DHA to IBA. 6 a.m., 8 a.m., 6 p.m., 9 p.m., weekend, Sunday morning, Sunday evening, Sunday afternoon. Monday at 8 is going to be very different than Monday at 6. Sunday at 6 is going to be very different than Monday at 6 p.m. And what you want to do is you want to say, okay, after going through this travel experience for the last year, year and a half, 2 years, what is the path that is guaranteed to get me to IBA without getting late for my class? How do I make sure that I walk in on time? So if you go back to our example of writing, we spoke about King on writing. King says, if you want to write, read. Then we spoke about the recipe of writing haiku. Can we take these two patterns, read, write, and then the recipe of writing haiku, and apply it to the concept of, is there a recipe of writing a speech? Turns out there is. There is a recipe for writing a speech, and that is, tell them what you're going to tell them. So this is number 1. And then number 2 is tell them. That's number 3. And then tell them what you've told them. So tell them what not you are going to tell them what you have told them. There you go. Fixed it. So that's 3. So pattern. What is a pattern? If you want to write a speech, if I ask you to write a speech, the speech also has a recipe, and that recipe is step number 1, tell them. Step number 1, tell them what you're going to tell them. Step number 2, tell them. Step number 3, tell them what you've told them. That's the structure. 3 parts. Part 1, part 2, part 3. If you're doing a stage play, act 1, act 2, act 3. Act 1, tell them what you're going to tell them. Act 2, tell them. Act 3, tell them what you've told them. Act 1, मैं आ रहा हूं. Act 2, मैं आ गया हूं. Act 3, मैं आके अब जा रहा हूं. Right? 3 parts. Act 1, Act 2, Act 3. That's the recipe. What is this? Pattern. You go through the best speeches ever made in the history of mankind, and you'll find that there is a pattern. It may not necessarily be this pattern, but you'll find similar patterns. This pattern also comes through the structure of speech analysis over the last 200, 300 years. Who created it? Who identified it for the first time? I don't have an answer. If you're interested, you can look it up. So that's writing a speech. Design. I also call this algorithmic thinking because what you're really trying to do is trying to be responsive to the needs of your audience, right? Responsive to the need of your customers, of your users. It's a function. But design also is a function, is a question of what are you solving for. Third example comes from the field of investment management. How many of you have heard of Berkshire Hathaway? Investment man, in fact. Richest man in the world. Everybody knows who the richest man in the world is, but nobody knows, very few people actually are aware of the fact that he has a partner, and his partner's name is Charlie Munger. Now, Charlie's gone out and said something really interesting, and his statement, and this is one of his quotes, well-known, better-known quotes, is how much long-term advantage people like us have gotten by trying to be consistently not stupid rather than trying to be very intelligent. How does this apply to code? This applies to code because a lot of time we write code thinking that we're writing this code in a really intelligent, exceptional fashion. No. Don't try to be extra intelligent. Just try to be not stupid. Focus on not being stupid. And what's the advantage? The advantage is, in the world of investment and fund management, it is important to try not to be extra intelligent and focus on getting the basics right. The same thing holds true in the world of programming and coding. Focus on the basics. Get the basics right. Don't try to be intelligent. If you're intelligent, that is great, but go out of your way to make sure. Ask yourself this question: is this considered being stupid? Am I being stupid? Try not to be stupid. So if you look at the themes across the three themes that we looked at, right? If you go back here, if you go back to abstraction. Abstraction is focus. Where does this example come from? On writing. Who gave it? Stephen King. Famous author, lots of books, 50 years of writing career, wrote a book on writing. What's the essence of that book? If you want to write, read. What if you want to code? Code is also a function of writing. So then read. If you want to be a great coder, read. That's the essence. The original inspiration for this, the original muse for this is not from the field of computer science, but the concept is applicable, still same, common lesson. Number 2, decomposition. What's the example you picked? Recipe. Where's the recipe? Haiku. What's the recipe? 3 lines, 5 syllables, 7 syllables, lines or rhyme, include a kaiji or a cutting word, includes a kigo or a season reference. Okay. How does it apply to computer science? How does it apply to programming? How does it apply to computational thinking? Be concise. Be to the point. Be simple. There is beauty in being poetic, to the point and concise in 17 syllables and 3 lines. That's the lesson. That's the takeaway. To the point and concise. Focus on the core. Lesson number 3, pattern recognition. What's the element? Write a speech. Tell them what you're going to tell them. Tell them and then tell them what you've told them. 3 stages, 3 acts, 3 phases. And then finally, design. What is Munger solving for? What do portfolio managers, investment managers solve for? Not losing money. Trying to be extra intelligent loses you money. Trying to be not stupid, extra hard to be not stupid, saves you money. Trying to be extra intelligent hits your return. Trying to be not stupid ensures that you have at least some consistent return. And what's the essence? It's the strong swimmers who get into trouble and drown, not the weak ones. The weak ones stay away from the current. The strong ones get caught in the current. Okay. Why do I keep on taking these non-serious examples? Because algorithms are all around us, not just in the field of computer science. You have to open your eyes. You have to be willing. You have to be aware enough to realize that in the world around you, there are computational algorithms that work that we normally don't see or perceive as computational thinking, but they are. How did Munger came up with this rule of not being stupid? On focusing on not being stupid. That's the essence of Munger. Is about 90 years old. Munger is close to about, I'm guessing Munger is close to about 90 years old. At least 70 of those 90 years were dedicated to the profession of investment management. The essence of his lifetime of experience in the world of portfolio investment management is don't be stupid. Don't try to be intelligent. Try to be not stupid. Not stupid. Essence of Stephen King's experience. You want to write? Read. Essence of writing a haiku. Be concise, to the point, clear, in as little number, in a limited number of syllables and lines. Be concise, to the point, and clear in a limited number of lines and syllables. Okay, make sense? And then generalization. How do we generalize? Why is generalization important? It's important because of a long list of reasons. One of those reasons is we want to look at patterns and then see if we can reuse those patterns elsewhere. Pixar has a list of rules on making films and telling great stories, and it's called a list of 22 rules. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pixar has a list of rules. They call the 22 rules of storytelling. We only have 10 of them here. But let's take a look at these rules. Simplify. Start at the end. Be honest. Focus on the spine of the story. Finish. Version -1. Rewrites. Test your characters with trials. Try over winning. Audience over personal preferences. Now these are rules for storytelling, but they apply to code. Of course they do. Can you generalize them? Yes, to simplify. Simplify your code. Start at the end. Why? Why do you want to do this? Be honest. Don't try to be something that you're not. The spine. Focus on the structure of your algorithm. Finish. It's important to ship. You can't just sit and code throughout your life. You have to finish the work that you've been assigned and ship it. Ship it. Your first version will always go in the bin. So be ready for rewrites. Give yourself enough time so that you can read it in code the second time, the third time, the fourth time, the fifth time that you write it. Tends to be better. Test your character. Test your code with trials. What are trials? Boundary conditions, scenarios that you normally not think of, that will not be tested as part of your regular part of flow. Trying over winning. Winning is great, but much more than winning, trying is important. You don't have to win with every line of code you write, but you certainly need to try to write it, because trying is the path that ultimately get you to where you need to be. And then finally, audience over personal preferences. Don't do what you think is right for the users. Ask them. Don't do what you think would feel right to them. Ask them. Focus on their preferences rather than your own. That's Pixar Rules for telling stories as applied to the field of computer science. What about the field of computer science? And that's where we get into a discussion on the deeper dive of computational thinking. That will be part of our second lecture. Thank you very much.